Welcome back to the classroom. This is Mr. Wong. Today we're going to explain another exam question, this time from the 2013 HSC Physics paper. This is to help answer Module 5, Inquiry Question number 3, which is about motion in gravitational fields. So this is worth 5 marks. Let's have a look at the question. We have a planet that orbits the star at a distance of 1.64 astronomical units. Just for those who don't remember or don't know what astronomical units is, it's the distance between the Earth to the Sun. It takes about 590 Earth days to complete one orbit. Question 8. Why does the mass of the planet play no role in determining its orbital speed around this particular star? Well, what we know from Kepler's law, and you can also show this from the derivations, but from Kepler's law, r cubed t squared equals to gm over 4 pi squared. Okay, the mass of the planet is so small in comparison to the actual star, it doesn't influence its own motion. This big M here represents the large central mass. In this case, that would be our star, which demonstrates, so because as the planet's mass is much smaller, its motion is, or its orbital speed is dictated by the gravitational force of the star. Another way you could try and prove this is by equating gravitational force and centripetal force. As we know, both of them are related. So I'll show you another way of showing this. So Kepler's law is one way of showing it. But another way of showing it is just by trying to find the orbital velocity of the object. So let's say the planet has a mass of m. The mass of our star is big M. The reason why an object has orbital speed is because of a centripetal force caused by the gravitational force of attraction, right? Okay. So v in this case is the orbital velocity of the planet. If I solve for this equation, you can see how the two masses, the two little m's, cancel out the mass already. So just by that, it already demonstrates it can't be, or doesn't need to be accounted for its orbital speed. So m is cancelled, does not determine orbital speed of planet. But we can go further. We can actually try and solve for this whole equation. So get v squared equals to r times that over, cancels out with this r here. So we get this m gm over r, and then gives us v equals to the square root of gm over r. This v is our orbital velocity, or orbital speed, okay? Hence, orbital speed is not determined by little m. And that's another way you can prove it if you choose not to use Kepler's law. Okay. Next question. We have a satellite orbits the star with a period of 365 Earth days. How far is the satellite from the star in astronomical units? So in this one, we are using Kepler's law. Okay. Let's see. Okay. So if we actually look at this question, we can see that capital G we do have, but we don't actually have the mass of the star. So what can we do? We can actually rewrite the equation like this. R cubed t squared, and this will be for the planet, okay? So for our planet, and then we can look at our satellite, okay? Because this equation is the same as this equation here. We're using Kepler's law to say that if there are two satellite-like objects, so we have our star, and we have one satellite, we have a second satellite, the distance it takes and the time period that they take to make their orbit around this singular star is going to be in the same ratio as each other. Okay, so if it's a bigger distance, it will take a longer time. If it's a smaller distance or radius, it will take a quicker bit of time. So that's kind of the idea here. So now that we've set up our equation, we can do some substitutions. We know that the radius, or the distance, is 1.6 astronomical units for our star. And we know that the period for this movement is 590. We want to find this particular distance here. We know the time period of this one is 365 square. Oh, that should be cubed square. Okay. Okay, so let's rearrange our equation. It becomes r cubed for our satellite equals to 1.64 cubed times 365 square divided by 590 square. Okay, so what we can do then is cube our expression. So the distance of separation would be approximately in 3 sig figs 1.19 astronomical units. Okay, and that's how you do this question. If you found it useful in explaining Kepler's law or anything about orbital speed, hit a like, subscribe if you haven't done so already, and I'll see you next time.